Hello, and hope you're having a wonderful day today, and thank you for joining me in this video where we're going to be having a look at this integral here. So let's not waste any time and let's delve right into it. Okay, so at first glance, this integral looks quite tricky because you don't know if you want to do u-sub, integration by parts, or any other techniques. You're not sure if they're going to work. So whenever you have a trigonometric function like this, I'd say try the King's property because it's most often guaranteed to work. Okay, so what is the King's property, you may ask? Well, the King's property states that the integral from alpha to beta of function of x dx is equal to the integral from the same bounds, alpha to beta, of function of alpha plus beta minus x dx. Now, you may ask, why is this? Well, let me show you a quick proof of it. Alright, so we're going to let x equal to alpha plus beta minus u. So dx obviously equals negative du. As x is approaching alpha, u approaches beta, and as x approaches beta, u approaches alpha. So using this, if we transform the integral above, we're going to get if we transform this integral here, we're going to get the integral from beta to alpha of function of x, which is this, alpha plus beta minus u, and then we have to multiply it by negative du. So let me put the negative there, the du here. Now, because of this negative, we can swap these two bounds around. So if we swap them around, alpha is going to come here, beta is going to come here, and boom, there we go. We've just proved the King's property. Alright, so now we have to utilize this property to solve the above integral. Okay, this integral here. So let's use the King's property. So I of n is going to be equal to the integral from 0 to pi over 2 of 1 divided by 1 plus tan of pi over 2 plus 0 minus x, and all of this to the power of n dx. Alright, so this inside bit, let's just tidy it up a bit. It's just going to become pi over 2 minus x. Alright, so now we wonder, what is tan of pi over 2 minus x? Well, that's where triangles come in handy, especially right angle triangles. Alright, so let's let this angle be x here. For this angle here, this is the opposite, this is the adjacent, this is the hypotenuse. Now this angle here is going to be equal to pi by 2 minus x, because this is 90, this is x. These two added together is 90 plus x, or pi over 2 plus x, and angles in a triangle add up to pi, so we have pi minus pi over 2 minus x, which will give us pi over 2 minus x. Okay, so now tan of x is equal to opposite divided by adjacent. Okay, tan of pi over 2 minus x is going to be equal to adjacent divided by opposite, because for pi over 2, the adjacent for this angle is the opposite for this angle here. Okay, alright, so what is adjacent divided by opposite? Well, if you guys remember, cot of x is going to be equal to adjacent divided by opposite. So that means tan of pi over 2 minus x is simply cot of x. And cot of x is 1 divided by tan of x. And we'll be using that later. Alright, so let me rewrite the integral from 0 to pi by 2 of 1 divided by 1 plus cot to the power of n of x dx. Now, like I said before, cot of x is 1 divided by tan of x. So let's rewrite cot of x. So it's 1 divided by tan to the power of n of x. Now let's just multiply the top and bottom by tan to the power of n of x. Okay, so we're gonna multiply the bottom by tan to the power of n of x. We get this, and we multiply the top by tan to the power of n of x. We get that. Alright, and this looks suspiciously similar to the original integral, okay, but it's got an extra tan to the power of n of x on the top. Now this is a technique that I love to use, let's see what happens if we add these two integrals together. So I sub n plus I sub n, which is 2I sub n, which is equal to the integral from 0 to pi by 2 of tan to the power of n of x over tan to the power of n of x plus 1 dx, plus the integral from 0 to pi over 2 of 1 over tan to the power of n of x plus 1 dx. Alright, let me cross this out here. Alright, so we have this at the moment. So now, because these bounds are same, we can combine these integrals even more. So these integrals are going to become tan of x to the power of n plus 1 over the denominators. And thankfully the denominators are the same. Tan to the power of n x plus 1 d of x. And I hope you guys have noticed it. Let me just add it to I of n here. Those two are the same. Yep. So what's going to happen now? They're going to get cancelled down. That's what's going to happen. So this is going to equal the integral from 0 to pi over 2 of 1 dx. And that's simply x evaluated between 0 to pi over 2. And obviously 0 is 0, pi over 2 is pi over 2. So 2, let me change the color. So 2I sub n is equal to pi by 2. Therefore, I sub n is equal to pi by 4. And that is our grand answer. And what do you notice? Well, you notice a constant answer. So whatever value you put for n, the value is always going to be constant. It's always going to be pi by 4. Thank you for joining me in this video. And that's it for now. Hello, and